We all know what the radius and diameter of a circle are. The radius being the distance from the center and the edge of the circle, and the diameter being the distance from one end of the circle to the other. And we can use these lengths to find the perimeter and area of the circle. The perimeter is equal to 2 pi times the radius, and the area is equal to pi times the radius squared. We also see that the perimeter is equal to pi times the diameter, and we see that the area is equal to a quarter pi times the diameter squared. We also see that the diameter is equal to 2 times the radius. The radius and diameter are only ever talked about in terms of circles, but today I'm going to show you how to apply them to other shapes. In this circle I mark 4 points, P1 to P4. We see that the distance P1, P2 is equal to the diameter. We also see that given 2 points in the circle, the distance between those 2 points is never greater than the diameter. Let's do the same for the quadrilateral, marking 4 points Q1 to Q4. We can see here that the distance Q1, Q2 is the longest distance we can find within the quadrilateral, and that no other pair of points will have a distance greater than the distance Q1, Q2. Doing the same for the triangle, we mark 4 points R1 to R4, such that R1, R2 is the greatest distance in the triangle, so that no other pair of points has a greater distance than R1, R2. We see that Q1, Q2 and R1, R2 have the same property as the diameter of the circle, in that they are the greatest distance found between 2 points in their respective shapes. We can therefore define the diameter of a given shape as the greatest possible distance between 2 points within the shape. Now for the radius. Earlier, we saw that the diameter of a circle was equal to 2 times its radius. Therefore, we could define the radius of any given shape as half its diameter. But this is boring. It would be more interesting to find a unique property of the radius that we could apply to any other shape. To find this property, we'll have to use calculus. In general, the derivative of the function a times x to the n is equal to na times x to the n minus 1. And applying this to the area and perimeter formulae from earlier, we see something interesting. Plugging in pi for n, r for x, and 2 for n, we see that the derivative of pi r squared is equal to 2 pi times r, which is the perimeter. Thus, the derivative of a circle's area with respect to its radius is equal to its perimeter. Now, if we look at the area and perimeter formulae with respect to the diameter, we see something different. Plugging in a quarter pi for a, d for x, and 2 for n, we see that the derivative of a quarter pi d squared with respect to the diameter is equal to a half pi d, which is not equal to the perimeter. This property is unique to the radius, so we can define the radius of any shape as the length r that satisfies this derivative. So how can we find the radius of a shape? To start, we'll begin by finding the derivative of the area of a right triangle with respect to its height. Here we can see, by extending the height a small amount, we increase the area by this small strip at the bottom. And we label the difference in height as delta h, and the difference in area as delta a. By approximating the extra area as a rectangle, we see that delta a is approximately equal to b times delta h, thus seeing that delta a over delta h is approximately equal to b. So we should expect that the derivative of the area with respect to the height is equal to the base. By labelling this angle here theta, we see that tan of theta is equal to base over height. Therefore b is equal to h tan theta. The area of a triangle is equal to base times height over 2, and substituting our formula for base, we see that the area is equal to h squared tan theta over 2. And by applying the derivative power rule from earlier, we see that the derivative of the area with respect to the height is equal to h tan theta, which is equal to the base, therefore confirming what we expected. We can apply this to any triangle by splitting a triangle into 2 right triangles with a height of h and bases of b1 and b2. we can label the areas of these two right triangles as A1 and A2. We can see that A1 plus A2 is equal to the total area, and B1 plus B2 is equal to the base. Given that we've shown that for a right triangle, the derivative of its area with respect to its height is equal to its base, we see that dAn over dH is equal to Bn for any n. Here we will use another rule of derivatives, that being that the sum of the derivatives of two functions is equal to the derivative of the sum of those two functions. Using this, we see that the derivative of the area with respect to the height is equal to dA1 plus A2 over dH, which is equal to dA1 over dH plus dA2 over dH, which is equal to B1 plus B2, which is equal to the total base. Thus showing that for all triangles, the derivative of its area with respect to its height is equal to its base. From here, we can actually find the radius of a triangle. First, we label the three sides S1, S2 and S3, and then we inscribe a circle in the triangle. We then extend lines from the centre of the circle to the vertices of the triangle, and we label the radius of the circle R. We can see that the three lines extended from the centre of our circle splits our main triangle into three smaller triangles. And by analysing those triangles, we see that each has a height of R and a base of Sn. Applying the derivative formula from earlier, we see that if we derive the area of this small triangle with respect to R, we get S of n, which is the length of one side of the big triangle. Here we make a note that the total area is equal to A1 plus A2 plus A3, and the perimeter is equal to S1 plus S2 plus S3. And by using the fact that the derivative of sums is equal to the sum of derivatives, we get that dA over dr is equal to d A1 plus A2 plus A3 over dr, which is equal to dA1 over dr plus dA2 over dr plus dA3 over dr. This is equal to S1 plus S2 plus S3, which is equal to the perimeter, thus showing that deriving the area of a triangle with respect to the radius of its inscribed circle, we get the triangle's perimeter, thus showing that the radius of the triangle is equal to the radius of its inscribed circle. This is true for all polygons with which you can inscribe a circle, the circle being tangent to every single side of the polygon. Every such polygon can be split into triangles like this, where each small triangle has a height of r, and the sum of the bases is equal to the perimeter of the polygon. Thus, the radius of each of these polygons is equal to the radius of its inscribed circle. But what about shapes without such an inscribed circle, like this rectangle here? For all 2D shapes, the perimeter is a one-dimensional measurement, and its area is a two-dimensional measurement. Therefore, the perimeter is proportional to the radius, and the area is proportional to the radius squared. We'll use little p and little a as the proportionality constants. Applying the derivative power rule to the area formula we have here, we see that the derivative of the area with respect to r is equal to 2 times a times r to the power of 2 minus 1, which is 2ar. And by our definition of radius, p is also equal to 2ar. By substitution, we get that pr is equal to 2ar. Thus r is equal to 2ar over p. Multiplying both the top and the bottom by r, we get that r is equal to 2ar squared over pr, which is 2 times the area divided by the perimeter. Thus we have found a general formula for the radius of a 2D shape. Let's see if this formula works. Here we have a rectangle with side lengths of 1 and 2. Thus its perimeter is 2 times 1 plus 2, which is 2 times 3, which is 6. And its area is 1 times 2, which is 2. By plugging these numbers into our radius formula, we see that the radius should be equal to 2/3. We see that 6 is equal to 9 times 2/3. Thus the perimeter is equal to 9r. We also see that 2 is equal to 9 over 2 times 2/3 squared. Thus the area is equal to 9 over 2 times r squared. By applying the derivative power rule to this area formula, we see that the derivative of the area with respect to r is equal to 9r, which is equal to the perimeter. For a general rectangle of side lengths a and b, we see that r is equal to 2ab over 2a plus b, which is equal to ab over a plus b. Now let's look at a triangle with side lengths a, b and c. The perimeter is equal to A plus B plus C, and we can define the semi-perimeter as half the perimeter. And by Heron's formula, we get that the area is equal to the square root of S times S minus A times S minus B times S minus C. Thus we see that the radius is equal to 2 times the area over the perimeter, which is 2 times the area divided by 2S, which is the area over S, which is the square root of S times S minus A times S minus B times S minus C, divided by the square root of S squared, which in all is the square root of S minus A times S minus B times S minus C divided by S. Thus we have a general formula for the radius of a triangle. Lastly, let's double check that this works for a circle. We'll define the distance between the centre and the edge as A. Thus we get that the area is equal to pi A squared and the perimeter is equal to 2 pi A. Plugging these into our radius formula, we get that the radius is equal to 2 pi A squared divided by 2 pi A. After some cancelling out, we are left with just A. Thus the radius of the circle is in fact the radius of the circle. I hope you all enjoyed the video. Leave a comment if you have any insights or queries, and subscribe if you're interested in more strange mathematics like this. Have a nice day.